Here at Sirius, we specialise in measuring physicochemical properties of drugs. That's properties like pKa values, log P values, solubility, dissolution rates, and these are useful in trying to decide what molecules are going to do in the human body. Not their effect as drugs, but things like will they be absorbed, will they be transported around the body, will they stay in solution, will they be precipitate out, things like this. You need to know that because you could waste an awful lot of time developing molecules with unsuitable properties which would just never make it as drugs on the market. This is the real heart of the technology, the thing that took us several years to develop. And in here is a lot of very important parts. We'll start with this one at the front with the white cap. This is a pH electrode. This is one of the smallest pH electrodes ever made. It's made specially for us, and we need very accurate measurement during these titrations in very small volumes. Also in here we have a stirrer. You can see at the left hand side with the brass top and the little piece at the bottom. That's a stirrer. We can stir up to 10,000 RPM or down to very slow speeds, all computer controlled, stirring during the experiment to mix the sample and titrants and the octanol. Then on the right hand side we have this ceramic. You can see it looks a grey colour with a brass thing on the top. This ceramic contains 6 tubes brought from these 6 dispensers. Each of these tubes carries a liquid and dispenses it into the solution during measurement, and these do the job of a burette in a normal titration experiment, except that these have very small volumes. The smallest volume we can get from one of these dispensers is 4/10,000ths of a milliliter. It's a tiny little volume, hard to visualize how small it is. Well, also in here we have this probe. This is an ultraviolet dip probe. This brings ultraviolet light through a tube, puts it onto a quartz mirror, bounces it back, and it can look at changes in light absorbed during the experiment. All of these components, plus a couple more, these are required during the measurements we make, but these work very well, and they are now to be found in laboratories all over the world that are using this technology for drug phys-chem property measurement.
Sirius Analytical receives samples for analysis from clients that include pharmaceutical companies and university research departments, both in the UK and around the world.
So what sort of samples do people send to us? Well, broadly speaking, they come in 2 classes. There are customers who send us perhaps hundreds of samples, all of different structures, but all only slightly different, with small substitutions. And what they'll be looking for is, for example, which substitution will give us the molecule with the optimum log P value. Not so high that the drug gets stuck in membranes, not so low it gets excreted immediately. What is the right target log P for them? So they'll be sending us a range of molecules to study. Now we get another class of customer. They've already decided which molecule they want to bring to market, and they're looking to make an optimum formulation. So they perhaps will send 1 or 2 samples, and they'll want us to make very careful measurements, perhaps under a number of different conditions of things like pKa, log P, solubility, dissolution rate. These are particularly important for the formulation customers, and their goal is to produce an optimum formulation.
The package delivered by Royal Mail is taken to the laboratory. It's opened and the form listing details of the sample and the measurements to be made is checked. The labelled tube containing the compound to be measured is taken out of the protective packaging, inspected and stored for analysis later. Details of the compound and the client's analytical requirements are logged on a computerized system. Data gathered during the analyses will also be logged, along with the final report to the client. No matter what property is going to be determined, the first step is to measure a quantity of the compound for analysis. The sample needed is tiny, less than 1 milligram. The sample is taken and placed in the instrument. The program to instruct the robot to make the necessary measurements is chosen. The whole process is computer controlled. The sample tube is moved into position and the probes and stirrer are washed. Here are the components of the analysis unit. On the left, you can see the tiny stirrer. The glass bulb is a pH electrode, and behind it is a probe that detects changes in UV absorbance. On the right, enclosed in a ceramic sheath, are 6 tiny tubes that deliver measured volumes of different liquids from reservoir bottles. In this first experiment, pKa is being determined. The analysis unit is given a final wash and lowered into the sample tube. A known volume of water is added, usually 1 to 2 centimeters cubed. The pH of the liquid in the sample tube is measured and recorded, and potassium hydroxide solution of known concentration is added slowly. Data can be displayed in various formats. The one you are likely to use in the lab is a graph of pH against volume of alkali added. From these data, the special software calculates an accurate value for pKa. In this second experiment, log P is being determined. The analytical unit is positioned in the sample tube. Known volumes of water from the white dispenser and octan 1-ol from the yellow dispenser are added. The mixture is stirred and acid from the red dispenser is added slowly. The instrument makes measurements and the software determines log P from the data. A previously measured pKa value is used in the calculation. The software produces a lipophilicity profile. This shows how the tendency for the compound to dissolve in fat rather than water changes with pH. In this final experiment, the solubility of the compound is determined. A measured volume of water is added to the compound in the sample tube. A measured volume of potassium hydroxide solution is added to dissolve the compound. Now acid is added slowly and the UV absorbance of the mixture in the sample tube is measured. You can see when a precipitate forms, but the UV probe is more sensitive than the human eye. It can detect the very start of precipitation. You can see a marked change in the graph of UV absorbance. After the experiment, the software determines the solubility of the compound, again making use of the previously determined pKa value. It then produces a solubility profile that shows how solubility changes with pH.
After we've made the measurements, of course, we have to get the results into the customer's hands, and we do that by sending them a report. And of course, the data, we hold it here in the computer because it's a very big file. They just want selected information from that data, like what is the pKa value, what were the conditions of the experiment, and some graphs to show them what's going on. So we produce that as a report, we make a PDF copy of it, and we send the PDF to the customer by email.